right. First, I would like to welcome all of you today to our July webinar series that is hosted by the Fiber to the Home Council, MENA. Our welcome extends to our members and their partners, and we hope all of you join us if you are not in the council yet and you enjoy and benefit from today's webinar. I would like to thank as well our council member Dura-line in accepting our invitation to this initiative and leading the way with the three of special matter experts speaking during these webinars. Today's webinar is about fiber optic sensing with Dr. Paul Dickinson. Dr. Paul Dickinson is the Director of Technology Partnerships at Dura-line, a telecom industry veteran of over 29 years. He began his career as an AT&T Bell Labs materials research scientist developing new optical fiber cable material formulations before moving on to a variety of different positions within Lucent Technologies and OFS. His prior experience includes leadership roles in R&D management, optical systems engineering, technology transfer, and scale-up marketing and sales. 6 years ago, Dr. Paul joined Dura-line to develop and execute an enterprise business strategy and has since also focused on additional areas of innovative business development. One of his primary current initiatives involves global strategic planning and solution development of fiber optic sensing solutions in a wide variety of vertical markets. Dr. Paul earned his bachelor's degree in chemistry from Cornell University and PhD in polymer science from the University of Connecticut's Institute of Material Science. Dr. Paul, I'm very happy to welcome you today, and I believe I borrowed a few extra minutes of your time, so I will step aside and give you the full floor. We will leave all questions after our speaker finished the presentation. Welcome, Dr. Paul.
Thank you. Thank you. And a big thanks to the Fiber to the Home Council for the opportunity to present information today, which I hope you'll find both interesting and helpful. Also, good morning, good afternoon, and good evening to those of you who are able to join us live today. As was mentioned, I'm Paul Dickinson. I'm the Director of Technology Partnerships with Dura-line. And Dura-line is the leading global provider of conduit pathway solutions for datacom and other applications. Last Thursday, my colleagues also from Dura-line presented information on microtechnology, which is a novel installation technology. So I hope you find this presentation complementary to that one, and that it further enhances your knowledge and your ability to integrate exciting technologies into your planning and, most importantly, into your infrastructure. And for the interest of bandwidth, I'm going to shut off my video until we get to the question and answer part for the rest of the presentation. So let me jump right into it here. And just an overview, excuse me, on where we're headed today with our discussion. I'm covering a lot of materials today, and I hope to tie it all together at the end. First of all, I'm going to provide an overview of what distributed fiber optic sensing is, how it works, and the main markets and applications, along with the description of an organization that provides guidance and promotes the technology to the industry. Excuse me, I think I'll have a sip of water. Second, I'll review the state of the art regarding layer 1 conduit and fiber cable technology for building out infrastructure for any of those vertical markets that we'll mention. Then I'm going to discuss how combining both best practice infrastructure design and products along with distributed fiber optic sensing makes tremendous sense and maximizes the value for all the channels and end customers. And then we're going to go through several examples of how distributed fiber optic sensing is used in specific vertical markets and applications. And finally, I'm going to summarize, with the time remaining, some of the key takeaway points and offer my perspective on a few recommendations for your consideration. First, a brief introduction to any of you who may be unfamiliar with Dura-line. Dura-line is one of a number of companies within our parent company, Orbia, whose mission is to tackle very difficult world problems with the purpose of improving and advancing life around the world. Dura-line was founded nearly 50 years ago and is today comprised of about 2,000 employees with offices, R&D centers of excellence, and over 20 global manufacturing locations. As one interesting metric you may find pretty daunting, we produce over 1.4 billion feet, or I think that's 400 million kilometers of conduit annually for global distribution. And also, we're a founding member of the Fiber Optic Sensing Association, which we're going to talk about in just a few minutes. This map shows most of Dura-line's manufacturing locations around the world, including those in India and Oman. It's through this extensive supply chain that you're seeing on this map, and also customer focus, that Dura-line is the leading supplier of high-density polyethylene products and solutions in the world. So now let's dive right into it. Now that I've introduced Dura-line, I'll describe what distributed fiber optic sensing is and what it's capable of. At a high level, it enables monitoring of fiber optic cables from a single location using pulsed laser light. As a result of this, the monitoring is able to occur continuously, or 24 hours, 7 days a week. And we can think of the fiber cable as being a summation of thousands of discrete sensing points, with resolution and location accuracy as good as just a few meters or even less. And since it's based on fiber optic technology with a laser, it's passive and no power is needed along the length of the cable. And it's also important to realize, you see the three icons above, that there are several varieties of distributed fiber optic sensing, and there's some overlap between them depending on the application. We'll talk more about that later, but the three types, just to let you know what they are: distributed temperature sensing, or DTS, distributed strain sensing, or DSS, and then finally distributed acoustic sensing, or what typically called DAS for short. Based on the different types of distributed fiber optic sensing, you can actually have several systems running over the same fiber, depending on your hardware configuration. The final point I'll make is that it's an upgradable technology, since you can leave the fiber cable in place and potentially upgrade the hardware, software, or artificial intelligence for analysis. I'll also cover the means for upgrading the fiber cable later in the presentation, so that you can have that in addition as one other degree of freedom. This slide displays the wide variety of different vertical markets with fiber optic sensing that are used today, and those that are continuing to grow as the channels and end users become more familiar with capabilities and the advantages. So just to categorize them, you can see that there are manufacturing and production applications such as oil and gas well monitoring and industrial process monitoring, applications with piping distribution for assessment of integrity and temperature, applications in transportation, whether roads or rail, applications in power cable and electric grid monitoring, and applications in structural health of assets such as dams and bridges. Those that assess geological events such as earthquakes and landslides, and then finally the application of third-party intrusion, or what's typically called TPI, which can be standalone or also done in combination with these other applications. So distributed fiber optic sensing has varying degrees of penetration in all these markets. Some are very well established, such as the pipeline, perimeter, border security, and rail. Others are growing in use, such as roads, energy networks, and water conservation. A few are not even on the list, and I know ones that are very near and dear to you, such as telecom networks and also smart cities down the road. So how does it actually work? The way it measures vibration, temperature, and strain is based on the interaction between laser light and the glass in the fiber. As the laser light travels through the fiber, the main pulses proceed forward to the receiver, which is the basis of data communication that you're very all likely familiar with. But as the light travels forward, a small fraction is backscattered through interaction with the glass. The amount and the type of backscatter changes along the length, depending on what's going on in the environment that's near the fiber cable. Also, there are different types of backscatter processes that can be used to extract the information. So what's important to know is when the backscatter signal is received at the same location where the laser pulse originated, it can be analyzed and interpreted to understand what's going on in the external environment based on strain, temperature, and vibration. And then finally, using reference libraries and artificial intelligence, the software can eliminate background noise and environmental conditions that are not of interest, and it can focus on the occurrence of the ones that are, leading to system integration, alarms, and actions to be taken. So in the picture on the right, you see hardware placed in the middle of a pipeline. This could be an oil, gas, water, slurry pipeline, and the fiber cable adjacent to the pipeline heading off in both directions. Should the pipe develop a leak, even as small as 1 millimeter, the noise of the escaping material and the changing temperature of the local environment as a result of the escaping material would be identified by the distributed fiber optic sensing, and that would lead to alarms before more damage could occur. On another important point, while specialty fiber and cables are available and they can be used to enhance sensitivity when it's appropriate, it's comforting for all of us to know, and you'll see why this is important later on, that there is great success just in using traditional telecom fiber cables for most of these applications. The benefits of distributed fiber optic sensing are numerous. One set of hardware can reach distances greater than 50 miles or 80 kilometers. The entire length is scanned in seconds, leading to real-time reporting and therefore very fast response. As I'd already mentioned, you can locate environmental events occurring with resolution down to a few or even 1 meter, which gives you precise locations. Also, it's all dielectric, which means it's centrally powered only for the hardware, not down the fiber cable, so there's no risk of sparking. And as with any fiber cable system, there's almost zero maintenance if it's properly installed and protected during its operational lifetime. And as we'll talk about when we discuss the advantages of careful conduit selection and design, you can add additional fiber to the original sensing cable and also additional cable to the adjacent right-of-way pathways so you can have other datacom uses above and beyond just sensing. In this chart, along the top of the x-axis, you have applications we referred to just a few slides ago. On the left side, or the y-axis, you have the types of distributed fiber optic sensing we just discussed: DAS with acoustics, DTS with temperature, or DSS with strain. Within the chart, you'll see numerous types of events or types of monitoring that can be identified. Now, you can certainly go back in the archived YouTube presentation and review this in more detail. In the interest of time, let's just go through one application example. I'm going to pick the one called transport monitoring, here focused on railroads. So using DAS, you can monitor the location of the train, you can identify speed, listen for any track conditions such as partially broken track or wheel problems that can cause damage, quickly identify a rock fall or earthquake to stop the train, and even, and this is not even listed, prevent pedestrian hazards or third-party intrusion. Using DTS, you can monitor temperature and alert for fires in the tunnels. And using DSS, you can monitor for landslides that have already started and also assess strain conditions along the track. Again, I encourage you to go back to this slide in more detail. We don't have time today. Once we send out the webinar YouTube link, and just look at all the applications here. Now, with all these existing and developing vertical markets, applications, and opportunities, there was a strong demand, just the same kind of demand that created the Fiber to the Home Council. There was a strong demand for an organization to develop and provide technical information and guidance in this field. So the Fiber Optic Sensing Association, or called FOSA for short, was established in 2017. The objectives include promoting DFOS across many markets and providing education on the benefits of this technology through several different avenues. One is technology awareness, the other is public policy, and then also promotion of the value of the solutions. Now, FOSA has an interesting history. It's affiliated with the Fiber Broadband Association, which is an all-fiber trade organization in the Americas, which in the Americas was previously named the Fiber to the Home Council. The members collaborate regularly and organize and manage activities both themselves and also with external engagement from interested third parties. Membership's open to companies associated with distributed fiber optic sensing. So if you're interested after this presentation, please reach out to me and I'll put you in touch with our executive director for consideration as a member, and also to discuss the process of becoming a member. I just wanted to show you a quick glimpse of the member companies that are currently involved in the event. You may want to consider whether your company's right or a good fit, either now or in the future. You'll see that in addition to Dura-line, which was a founding company, we have global fiber optic and cable providers such as Corning, OFS, and Prismium. We have installation companies such as Ditch Witch, and of course, multiple companies who manufacture and provide the hardware, software, algorithms, and artificial intelligence required to make distributed sensing interrogators that enable DAS, DTS, and DSS to work. Now, we're going to come back to it, But briefly switching from distributed fiber optic sensing to infrastructure, I want to discuss the needs of broadband, datacom, and digital assets as we consider the future of modern infrastructure and smart cities. You'll see how this relates to fiber sensing later on. The basic backbone of most fiber optic cable systems through the world starts with the use of conduit infrastructure. Whether it's the proliferation of 5G, autonomous vehicles, or other data-intensive applications, broadband needs continue to climb at an unpredictable and, frankly, an accelerating rate. In addition to long-haul routes, such as in telecom or highways or rail, it's important to realize that the backbone of fiber systems in the world is extremely extensive and interconnected. This simple illustration, or maybe it's not so simple, of all the linkages for fiber cable in a city displays both the underground and the aerial connections that provide this fiber backbone. If you look carefully, you'll see conduit between central offices and wireless towers, along roads, along electrical lines, whether they're underground or aerial, between and inside buildings, for drops to the home and commercial locations, and not even displayed here are the long connections for rings around cities and for connections between cities. The simple main point I want to drive home is that fiber cable's everywhere, and that everywhere fiber cable is, there's also conduit pathway. In modern new build construction, it's the conduit pathway that's usually designed first and installed prior to the introduction of the fiber cable. For decades, conduit's been the preferred manner of installing fiber cable underground, and now even in aerial applications. Many of us are likely unfamiliar with the advantages of using conduit, so it's helpful to review some of the main reasons why conduit's used routinely as an integral part of the datacom system using fiber optic cables. Let's briefly look at each category, starting with the dark blue triangle named Installation Advantages, and move clockwise around the graphic. First of all, it's easier to install as it can be put in section by section between access points, with the fiber cable later air assisted or pushed or pulled as in a continuous run. It's also easier to handle unexpected changes in the route, such as having to go around an obstacle as compared to directly placing fiber cable. In addition, the continuous run of fiber cable helps reduce the cost of splice points and improves the fiber loss budget for the total system. And also, the conduit itself can be locatable, which allows the fiber cable to be constructed with only non-conductive dielectric materials. Now let's move on to the protection of fiber, which is here in green. The conduit provides mechanical protection of the fiber cable, both during installation of the cable and also over the entire lifetime. Typically, direct buried fiber cables require additional design enhancements to withstand environmental conditions, whereas the conduit can provide that environmental tensile and crush protection itself. This enables the fiber density to increase significantly for a given OD cable. We see that with the smaller and smaller high-density microcables. Conduit also provides, and this is here in purple, a permanent pathway for upgrades and changes whenever you need to make them. For example, you can remove and change out a fiber cable that's damaged or swap out with improved technology, or you can simply use the additional empty conduits for increasing capacity. You can also reroute the conduit pathway if there's a change in route. Dig Once legislation that passed in the US and is growing in popularity on roads and cities, and which we'll discuss in just a few minutes, is right in line with this. Regardless of the application, it benefits every asset owner to plan for future unknowns and all demands on their networks. We're potentially installing for fiber optic sensing. There's also additional communication needs here listed in yellow, which can be accomplished in parallel using the same cable or cables and other conduits. This could be for applications that are in telecom, for cameras, for data transfer, security, and of course, providing redundancy. And then finally, to wrap up here, there's revenue opportunity, which is very important as we build out our cities. And this is in light blue, which enables network and right-of-way owners to use the empty pathways to grant access to difficult right-of-ways or be leased to carriers. So in sum total, on this complicated story here with the graphic, but a very important one, by literally only digging once and putting in multiple microducts, we can take full advantage of the new high-density microcables that fiber cable providers are shrinking and improving year over year. It's also important to realize there are several types of conduits, so we know what options are available. In a more traditional system, 1, 2, or 3 standard conduits could be installed together, as you see on the left side of the page. However, the outside diameter of these conventional ducts is quite large compared to the smaller outer diameter microducts seen on the right. While these large dimensions, perhaps 1¼ inches or 2 inches in diameter, are still used in the industry, they were developed at a time when fiber cables were much larger diameter with lower fiber density. Since typically only one cable is placed per duct, they actually limit the number of fiber cables that can be placed in right-of-ways. The smaller diameter microducts on the right side of the package are designed to take advantage of the newer fiber density microcables that have smaller outer diameter. Amazingly, there are 288 and 432 fiber count cables on the market now that are on the order of as small as 8 or 10 millimeters in diameter. So by sizing microducts for better space utilization, you can achieve much better overall fiber density in any right-of-way space. When these smaller microducts are packaged together on the one sheath at the factory, we at Dura-line call the conduit future path. As you can see, there are combinations of future path all the way from 2 microducts under a single sheath to 8 or more microducts under a single sheath. Finally, there are also hybrid designs. This one is called future path hybrid, which combines traditional conduit sizes such as 1¼ inch, 1.5 with 1814 or 2216 millimeter sizes. This very popular design enables different cable sizes to be used in the same right-of-way and in the same pathway. Now, with this slide, I want to illustrate that no matter what the end market application listed along the bottom, there are conduit and accessory types that are designed to meet the specific needs of the application. So it's important to become familiar with all the varieties, whether you're designing or installing a fiber network for datacom needs, or for sensing, or even more ideally, for a combination of both sensing and datacom purposes. The concept of dig once that I previously mentioned earlier is an important term to become familiar with. Dig once refers to digging one time for 2 or more projects and enabling future upgrades to occur without incurring additional high labor expense. By coordinating the timing of other construction, such as that of roads or utilities, a tremendous savings in labor can occur. Furthermore, combining dig once with microconduit and microfiber technology maximizes the use of existing right-of-ways, and it maximizes future upgrade paths and additional datacom purposes. And then finally, and we're tying things together today in this talk, right? Finally, by further combining this cost-effective dig once concept with proper installation with distributed fiber optic sensing, you can provide the most current and future customer value. And we'll talk about more of that in a few minutes. Now, we're going to start to tie it all together. So tying together the concept of distributed fiber optic sensing with modern infrastructure design and build using modern conduit technology that I just showed you, along with dig once installation timing and maximize use to your right-of-ways, the vision here I want to leave with you is to consider a total system solution approach where you integrate products, you integrate installation technology and sensing technology together for maximum benefit now and also maximum flexibility and benefit in the future. So on this page, you see the combination of integrating modern conduit technology with fiber cable and sensing interrogator hardware and software to address the markets we mentioned earlier: power and telecom, security and defense, pipelines, rail and road, and oil and gas, and many more that are continuing to develop. Also now, going back to just distributed fiber optic sensing, you can see that an integrated solution is possible. This slide illustrates, for the application of third-party intrusion, or TPI as I called it earlier, how identification of the occurrence of excavation, vehicles, and personnel can be linked to a command control system that provides alerts to control rooms, mobile devices, automating of cameras to get visual identification, or shutting down processes as needed. The point is that distributed fiber optic sensing can be just one critical component in an integrated system that does much more. As I stated earlier, while specialty fiber and fiber cable can be used for unique applications, most sensing interrogator companies, the ones you saw listed in my FOSA member company slide some time back, have great success using traditional telecom type fiber optic cables. For that reason, I think it's super exciting to realize that the billions of feet or meters of already buried fiber cable and conduit all around the world can be considered for use with fiber optic sensing, if it's appropriately placed in the ground or aerially as per the needs of the application. This slide simply indicates that sensing can be done either with a direct buried fiber optic cable or in a fiber optic cable that's located within conduit. In addition, the fiber cable can be all dielectric, in other words, containing no metal, or armor jacketed. So there are unique fiber and cable designs that may enable even higher degrees of sensing. But the important point for you to know today is that most designs, if located close enough to the environment to be measured, will work extremely well and exceed the needs of any commercial application. That also means, however, and this is very important, that for any new build, greenfield construction, the end user should make every attempt to design their distributed fiber optic sensing network in combination with a concurrent or future traditional datacom network to use the best information possible for their maximum advantage. What that means for new construction is that we should consider the total system solution by first locating the pathway of the route, if possible, within reasonable range of the asset to be monitored and also at an appropriate depth, selecting a conduit and fiber cable combination that will enable sufficient sensitivity, incorporating, as I described earlier, dig once construction practices and timing to save on initial labor costs, and then maximizing your conduit pathways in your right-of-way space to not only save on future labor costs, but also to provide scaling and replacement flexibility. Before I summarize, I think it's very important for you to see some applications. And so that we leave some time for questions, I want to change directions once again and quickly show you several examples of distributed fiber sensing applications in action. So these are the types I'll go through today. Many of these slides have been provided by FOSA member companies for illustrative purposes. Well, we could have an entire talk just about these examples, but I'm going to talk about pipeline monitoring, perimeter security, road traffic monitoring, the monitoring of geohazards, electric grid, which is very, very important around the world, fire detection, and then train tracking and integrity monitoring. And then also, as we move forward, smart cities is on everyone's lips these days as we talk about the future of our cities. We'll see how this plays in smart city applications. So first, here's a pipeline example of a multi-conduit product being put adjacent to a 24-inch stainless pipe. I think this is an impressive picture. It's being directionally bored under a river so that it can be used to monitor the pipe. The two orange reels contain the conduit. In this particular case, there's two bundled FuturePath products. Each of the products contains 7 14mm OD and 10mm ID conduits bundled under one sheath. And again, this is put in coincident with the cable so they can monitor the cable for its lifetime. This example is a perimeter security illustration that shows how security can take on many different types, with the ability to detect gunfire, digging, and also vehicle and personnel intrusion. Also, there's a brief listing here of some of the markets where this is being applied: energy, government, transport infrastructure, private properties, and data centers. The color charts along the bottom show an illustration of what the activity actually looks like on the screen as it's being monitored by the fiber and sensing interrogator. The operator, however, does not need to interpret these screens, but simply receives an alert to take action depending on the location and depending also on the type of activity that I showed you on the slide. This colorful chart shows the graphical user interface for a highway traffic monitoring system. From this, and with appropriate alerts, the user will be notified of traffic speeds along the road, travel times, where there's congestion, and also very rapidly for vehicle counts and accidents. This example shows the value of monitoring structural integrity of assets, such as dams and levees. In this particular case, strain sensing, or DSS, can be used to monitor deformation and also, very importantly, alert the population to a cable break or a wall failure well in advance of other technologies. This geohazard example that monitors for landslide alerts, tracks cable elongation by way of distributed strain sensing again, and also uses differential temperature sensing to look for water ingress and ground cracks. And again, a situation like this, you could provide very rapid alert. Electric grids are growing in popularity for DFOS sensing. This example uses this sensing to monitor power cables. And what this does is this enables detection of hot spots before they can cause catastrophic problems. Also, the current load of the power cable can be dynamically managed by monitoring the temperature of the conductor. And then finally, faults can be pinpointed if they occur for rapid response. I mentioned earlier that DTS, or temperature sensing, could be used for fire detection. This example shows applications up to 12 miles in length with 3-meter accuracy, where a fast change in temperature can create alert in less than 1 minute and save lives. And this has been very widely deployed in Europe and Asia. This train tracking example illustrates what a graphical user interface might look like based on distributed acoustic sensing. Positional accuracy of up to 10 meters is possible and provides for location, platform announcements prior to arrival, and quick notification of any incidents. In addition to train transport, the condition of both the metal rail, the track bed, the overhead electrification quality, and the rolling stock of the train or the wheels can be continuously assessed as an aid to prevent failures. I mentioned earlier that for many applications, there can be multiple types of sensing that can be implemented in parallel. In addition, for a given application, there can be multiple zones or applications for even a singular type of sensing. In this example, distributed acoustic sensing is being used not only to monitor the pig location or a cleaning device within the pipeline, but also to continuously monitor the pipeline for any valve leaks or leaks due to corrosion, and also in parallel to monitor for third-party intrusion events, such as trucks or personnel coming into unexpected areas at unexpected times, and for fence security around a protected region, such as a control room. Remember, this can all be done with one continuous fiber if the fiber is located near all the regions of interest. That's why the planning is so important. And now we'll come back again to smart cities, which can be described, in my opinion, as a collection of many of the applications and use cases we spoke of earlier. Smart cities are comprised of highways or roads, railroads, utilities, or facilities requiring security, and also structural assets requiring nonstop integrity. Nearly every city, as I hear, wants to become a smart city. Fast symmetrical broadband for business applications and the ability to provide internet access for all its citizens is one way to ensure the population stays within the city, both citizens and commercial businesses. And as you know, this is all the more important in the situation we're in now with the COVID virus. Everyone needs broadband and everyone needs symmetrical broadband. The key to fulfilling this dream is to build a robust conduit and fiber network infrastructure. But unfortunately, the capital cost of doing so is often quite high. One way to make this happen, in my opinion, is to both lower the total cost of ownership and enable additional means for monetization for the data. So to remind ourselves, and again, to kind of tie in all the concepts we're talking about today, this can be accomplished by proper modern conduit selection, best-in-class installation technologies, while using Dig Once principles. And this goes back to the talk we had last week on microtechnology and microtrenching, right? That's another thing that should be considered. And also designing in upfront the capability for distributed fiber optic sensing wherever it's possible and practical. So in short, by striving for a total engineered complete system solution. So we ask ourselves, where is distributed fiber optic sensing today? And what's the market opportunity? Well, here's a shaded map from the most recent update by FOSA in 2017 of over 1,300 installations around the world. And this is only for the FOSA member companies. This represents, however, it sounds large, but you'll see in context it's not, 20,000 miles or 32,000 kilometers of coverage. But as we probably all guess, this is only the beginning of the market opportunity. So in the US alone, I want to give you some statistics, just US statistics, but then you can extrapolate those for global. There's 6.8 million kilometers of road infrastructure with 47,000 kilometers of fast traffic highways. In the US, there's also 226,000 kilometers of railroads. And there's 800,000 kilometers of oil and gas existing pipelines. That's only a small, and as this group knows, small subset of the global oil and gas pipeline existing brownfield infrastructure. For oil and gas, it's worth diving in just a little deeper. In particular, installation technologies being developed that will enable conduit and fiber cable to be placed accurately and close enough to the outside of the already existing buried pipe without risk of damage to a live pipeline, so that any developing problems in these aging pipelines can be quickly identified. We talked earlier, pinhole leaks, corrosion, intrusion, people taking oil and gas. Once this technology is developed and you can actually put the conduit close to the buried pipeline safely, this is a very, very large global opportunity. And then there's fiber telecom, which most of us on this call are very involved in. The right-of-way miles only continue to grow with advanced wireless such as 5G and fiber to the home. For telecom in particular, the protection of critical assets from damage and the use of these assets that are already existing for other applications of interest provide a growing value proposition for distributed fiber optic sensing. So in summary, the market penetration is only beginning. Well, we've covered a lot of interrelated material today. So now's the time to summarize what we discussed. I'm just going to mention on these next two slides a couple key points that I think are the takeaway points and maybe the most important points from this presentation. The first is that distributed fiber optic sensing is a very valuable technology growing in both awareness and global adoption. Also, vertical markets and use cases for DFOS, or distributed fiber optic sensing, are expanding as new applications are explored and as end users simply begin to play with and experiment with this technology. I described the Fiber Optic Sensing Association. Please remember, this is a resource-rich global organization that welcomes new members if you're interested. In addition, it's important to realize that modern infrastructure for all the vertical markets we talked about and described for sensing are also moving toward the use of microtechnology using microducts. And then when we tie all these points together, combining microducts with sensing provides the end user with not only a flexible, scalable, future-ready fiber platform, but also for capabilities far beyond just traditional telecom and datacom use. Also, look at what you already have installed in your infrastructure over the years. Existing fiber cable and conduit systems can be utilized now for fiber sensing. And that to me is extremely exciting. Finally, when we consider future datacom infrastructure construction, or what I call green construction, it will benefit the end user, the system integrator also, to consider and plan for use of distributed fiber optic sensing in the network. Based on all this, what are my final few thoughts and recommendations? Let's together recognize, and I think we all do, that we cannot know what our optical bandwidth needs will be in the future. The magnitude and the rate of growth is uncertain, but we know one thing, it's always increasing. The best way to address this is to design in flexibility in your infrastructure and the ability to scale before you even begin installation. We need to build to accommodate this uncertainty by providing this flexibility. Also, design and build your network with dig once in mind to maximize asset use and to minimize total cost of ownership. And perhaps most importantly, and the biggest takeaway point at all, Make every attempt to combine modern infrastructure design and product selection with sensing opportunities, as this will lead to the greatest benefit. And the final point is, contact the Fiber Optic Sensing Association or your sensing expert company or Dura-line, and please reach out to me if you'd like to learn more. And with that, I hope you enjoyed this and I hope it was helpful. I'm going to turn it back over to the moderator and we'll answer some questions.
Well, thank you very much, Dr. Paul, for this informative webinar. We have a question from Mr. Carl asking about what spec of fiber is required. Can a spare fiber in an existing bundle be used?
Yeah, actually, that's a very good question, and we addressed that only later in the presentation. Yeah, that's the exciting thing about this. There are fiber technologies out there, fiberglass technologies, which are advanced and provide even greater sensitivity. There's also fiber cable technologies, which have been specifically designed to enhance sensitivity. But the real exciting thing, in my opinion, is that all the traditional datacom fiber cables, even whether they're gel filled or whether they're super absorbent filled, whether they're loose tube, whether they're loose fiber constructions, they can, in most cases, be used just fine for commercial applications of sensing. So the answer is, and this was one of the big takeaway points that I want to leave you with today, traditional datacom cables, the kind we use for telecom applications now, are the same cables that can be used for sensing applications.
Okay, and we have another question from Dr. Suleiman. Can you elaborate more on specialty fiber and application on DFOS?
Yeah, there are fibers out there that fiber cable providers have provided that have a grading technology or other types of specific fiber designs. The way fiber design is, oh, I'm sorry, I'll turn on my camera. Thank you for that. Yeah, I apologize. I did turn on my camera, didn't I? Yeah, there are fiber designs out there that are designed to enhance. I can't get into the technical details of those now, and many of those are proprietary, designed to enhance the sensitivity. And the way that works, because I'm kind of a glass guy too, is you change the refractive index of the fiber profile, or you do fiber grading technologies, and you can find those online. But and they enhance the sensitivity, they enhance the signal to noise, they enhance the dB sensitivity. But as I said just a second ago, the traditional G.652 cables that are used for datacom can be used for sensing. I hope that answers your question.
Yeah, so we have another question from Mr. Tariq. Are there any applications that not suitable for using microduct method?
Are there any applications not suitable? Okay, so when you look at downhole well monitoring, where the temperatures are very high and you're trying to monitor your fracking or your well location, and you can have all kinds of crazy materials down there, those applications for sensing require exotic metals. They're high temperature metals that can protect your fiber cable. Other than that, most applications where sensing is used or where datacom is used, as I said earlier, benefit tremendously by the use of conduit technology. And if they benefit from conduit technology, since microtechnology is just as crush resistant, just as uses the same installation technologies, micro trenching, directional drill, there's really no reason why not to use microtechnology if you're considering conduit technology at all. So my short answer is, I'm hard pressed to think of applications where you would have to have a buried fiber cable and not use conduit technology.
Okay, we have also another question from Dr. Suleiman. Could you talk about wireless sensing and how it compares to wired DFOS?
I'm not sure I caught that. Tell me that one more time, please. I'm sorry.
Could you talk about wireless sensing and how it compares to wired DFOS?
Wireless sensing. Okay, that's an interesting question. So as I mentioned earlier, distributed fiber optic sensing is passive. It's under the ground. It's going to think of it like an infinite set of microphones that are always picking up the environmental conditions. When it comes to wireless sensing, I'm not an expert in that area, But I would think that with wireless sensing, you're going to have not the capability to identify the location in such a precise manner, and also you're going to be limited to discrete sensing points. Whereas with a distributed fiber optic sensing, you're going to have a continuous run that, as I said, from one hut location going in both directions can exceed 50 miles or 80 kilometers. So that was probably a different talk for another day, where we'd have to do a direct comparison.
Okay.
But that's the best I can answer that right now.
Yeah. We have also a question from Mr. Power. How can we install dig once to the already deployed network? Can you elaborate more on how this will reduce 90% of the maintenance cost?
Absolutely. Okay, so there's two ways to look at labor here. I'll talk about the dig ones first. If you're already digging up a road and you're already doing utility work to put in right away, and then all you have to do is put in the conduit in the path you've already created by other labor costs. That's where the 90% comes in, because you're simply not using any labor at all except for the placing of the fiber cable in a path you're already putting in. So by timing your installation of the conduit technology with your other installation that your municipality, your city is already doing, that's where you're going to save the 90%. Now, the other labor savings, though, I want to mention regarding micro technology versus traditional conduit has to do with the fact that you're not digging up the same ground again the next time you want to upgrade. Let me give you a scenario. So one scenario is you're building out an infrastructure network, and you're saying, I want to put in fiber cable or conduit. And you decide to put in 2-inch conduit or 4-inch conduit for that matter. You put in one cable. So now you're digging up the ground. I think most of us know labor costs can be as much as 60 or 70% of the total cost. The product is a very small cost for the installation. 3 years later, you decide you want to upgrade your network, and the cable you have in is not enough, or you need an additional type of cable. You then have to dig up the ground again and incur the same labor costs again to put in additional conduit. The whole advantage behind micro technology and using a product such as FuturePath, the Dura-line calls it, is that once you put in a multi-channel product, let's say it's a 7-way 1814, 18 millimeters OD, 14 millimeters ID, you may only use up 1 or 2 of those pathways with a 288 or 432 fiber cable. You have all those additional pathways for upgrade technologies. The next time you go to put in your fiber cable, all you're doing is accessing your pathway, jetting it in with low labor costs. In that case, you're saving probably 60 or 70% or more of the cost of the installation. So there's many ways to save. And again, that's one of the main points. So thank you for asking that question. One of the main points is to think about the timing of your ongoing installation, and also think about how you can put in more pathways than one at the same time.
Perfect. So as said, sensor is passive component. At the same time, it is mentioned that it is upgradable. How this would be upgraded being a passive component?
Another great question. Okay, so there's lots of ways to upgrade, right? If you were putting in a multi-path conduit product, and you had open channels or open conduits you haven't used yet, then, and let's say you've got sensing equipment attached to a cable that's already in there, you could simply choose to keep that cable in there and jet in another fiber cable. Maybe you've got a fiber cable that has better acoustic properties, or maybe you decided down the road you need a better sensing, so you're going to use one of those fancy grating fibers that I talked about. So one way of doing it is to simply add an additional fiber cable in the existing pathways that have not been utilized yet. The other way to use it is that since a conduit is a permanent pathway, you can literally take out the cable you put in, use it somewhere else, and replace it with another fiber cable. And so you can upgrade either by taking out the existing cable you first put in, or you can upgrade by putting in an additional one in parallel to it. So there's lots of, the whole key here, and I know I keep saying this, is flexibility. Put in the flexibility, put in the scalability, so you can change the fiber count, you can change the fiber type, you can change the cable type without incurring those very aggressive labor costs.
Perfect. Mr. Omar is asking, what's the best fiber to use in sensor cable, G652D or G655 fiber?
Okay, now you're challenging my fiber days. G655 is a non-zero dispersion shifted fiber, I believe. If I'm wrong, you'll have to throw rocks at me. But G652 single mode fiber is the one that's most readily used in these applications. Now there are some applications with different types of scattering for short applications where you actually may want to use a multi-mode. I don't really want to get into that here. But basically, again, the real value here, and the key is, it's traditional single mode fiber. It's the same stuff we're using for datacom and telecom applications. So that's what you can use for sensing.
All right. Mr. Gaurav Singhal is thanking you for the session, and he wants to understand how cross-country border protection can be benefit using FOS, and what is the typical cost for of deployment per kilometer.
Okay, so I'll try to address both of those a little bit. So what the question I heard was, how is it used for border security? It's excellent for border security. I personally advocate for this over a wall any day. I think this is tremendous. A mechanical protection hat offers one thing. This offers so many benefits. So I can't name the border, but if you were designing a border, so to speak, maybe you would put in a couple runs of optical fiber. You would put it at perhaps 7 or 10 meters away from where you're trying to protect your border on either side. So what you would do is you'd have the capability by burying it under the ground at maybe a depth of less than a meter or meter. You'd have the capability for detecting a vehicle approaching or personnel approaching well in advance. There was actually, I participated in one experiment, this is crazy, where fiber cable was buried a meter under the ground, and we could actually detect digging about 100 meters away and walking probably 10 meters away. So as someone's approaching a border, you're going to detect the motion of the vehicle or the person walking along the ground, and you're going to be able to identify it's a person versus a coyote or a deer or some other entity. Also, by having a parallel router fiber on the other side, you could identify the location, which way they're moving, because you'll see one fiber get located first and then the other one later on. So you can identify direction. So that answers the question on border. Regarding the cost question, I'm just going to answer that generally. The cost for using multipath conduits is comparable for using traditional fiber conduits. The cost of the product is really inconsequential versus the labor cost. And the savings for total cost of ownership is tremendous. The cost of the sensing, I really don't want to get into on this talk because it depends on the application. But so contact me separately if you want to discuss that, but it's very, very cost competitive. I'll just give one example. So in transportation on roads, for example, my rule of thumb is that the cost of sensing along a road is about 5 times more using traditional microwave sensing and using cameras to do congestion sensing than it is to use a buried passive fiber optic cable. So that's not including, of course, installation of fiber cable and conduit. And that's why, again, one of the points of this talk is to combine the purposes together to save cost and labor even further. Many of the highways in the US already have fiber cable along them. So you simply have to take advantage of the existing fiber cable by attaching the interrogators to that. You don't even incur the cost of adding the fiber and conduit. So anyway, I talked around that. I hope that addresses most of the question that was asked.
Okay, so maybe Dr. Paul, I can share your email address if he needs more details about the cost and everything. This is okay with you?
Absolutely.
Perfect.
In fact, you're looking at it on the screen right now.
Yeah. Okay. So there's also another question from Mr. Muhammad. Is the false alarm generation, is it addressed in the monitoring systems and solved?
You're going to have to tell me that, say that one more time slowly. I missed that.
All right. So is the false alarm generation, is it addressed in the monitoring systems and solved?
Absolutely. Yeah. I mean, this technology would not sell if it was creating so many false alarms that people would be going to check out whether a rabbit had crossed the path or whether or not on an oil and gas pipeline, it was not really a leak, it was something else. The most important part of this technology actually is not the hardware. The hardware is advanced to the point with very thin line with lasers that it works very, very well and provides resolution. Most important part is the software. The companies that are very advanced in this technology have spent a decade improving the algorithms, developing digital libraries of what is an event and what is not an event. So when a test is done or a pilot study is done, it's done for a period of weeks or months, and events are generated either artificially or realistically, and you actually want to have nearly 95, 99, 100% accuracy in terms of identifying what a real event is not. The technology has progressed tremendously to the point where very few false alarms are generated. In fact, I'll just tell you one quick story. In the U.S., there is a pipeline test facility now has just been funded and approved that is going to be built for this purpose. So that was a result of FOSA's efforts in lobbying for that. So whether it's rail or whether it's oil and gas pipeline, very important to accurately represent what the realistic conditions are, to use the software and test for it, and to have very good accuracy. So the short answer is yes, the technology is very accurate and generates very few false alarms.
Yeah. So based on the vision of the applications that can be used using DFOS, and in case of having a new compound, and we are planning to use smart applications, does it mean that we need to cover all possible locations with fiber for current and future applications, and how to optimize this DFOS design?
That's a great question. So again, my pitch, what I'm trying to advocate today is you can't change where your fiber location is currently in your brownfield. I encourage everyone to go back and look at their network infrastructure and say, oh, wow, this fiber and cable is going by a critical asset, or it's going down a highway, and I want to use that for sensing. But most importantly, as you build out new networks, think about, you're not going to put sensing down every single road. You're only going to want to have sensing around the important things you want to sense. But there is a tremendous overlap between how you can design a datacom network and how you can design a sensing network. And you should try to maximize that overlap. That's my suggestion. Put the right depth in, put the right location in, reach out to Dura-line and discuss it, reach out to Fiber Optic Sensing Association and discuss it, but try to maximize the future ability to use it for sensing so that you can monetize that data and lower your overall costs.
Perfect. So, Dr. Paul, everybody is thanking you for this informative webinar. Mr. Omar, Mr. Jason Brabek, Mr. Garaf, Mr. Devash, and Mr. Shukri, Dr. Suleiman. By the way, he's one of the board of directors in the Fiber to the Home Council. And we have another question. Which are the top 2 applications of sensing for telecom service providers, and can they offer sensing as a service along with broadband, mainly to enterprise customers?
That's a great question. So as I said earlier in this talk, some applications are tried and true and have been used over a decade. Oil and gas, very, very solid application growing. Perimeter security growing. Telecom is just being explored now. So telecom, in my opinion, the easiest application is asset protection. So asset protection, if you have areas where you cannot afford, you don't have redundancy for your lines to go down, and you want your line to be constantly on 24 hours a day, 7 days a week, that would be the first application. When it comes to other applications, I would love to talk to you. Anyone who's building out a fiber network in telecom, reach out to me. I have ideas. I think the Fiber Optic Sensing Association has ideas. And I think this is a very good example of an end user who, once they start using the application for, let's say, asset protection, are going to develop other applications they think would be very valuable. So I also think that there's a very good possibility that this could be done occasionally as compared to it being done in a permanent installation manner. So I think the sky's the limit. I think we're just starting to understand that, and this is why this area is so exciting. We're just starting to grow in some of those applications.
Yes, definitely. One more question from Mr. Carl. Is the vibration sensing improved with tight bundling in the duct rather than loose?
Tight bundling in the duct. Well, in my opinion, that could be answered two ways. The cable design is important, so that the cable design should be considered. But in my opinion, microduct technology, based on the fact that you're going to have a smaller space in the conduit, is going to provide greater sensitivity than a traditional larger duct. So if I had to compare a 4-inch conduit or a 2-inch conduit relative to a micro conduit where there's better contact of the cable inside, better acoustic coupling, I would say that it would be as good or perhaps even better to use micro technology. That's my opinion. But I know that for almost any duct combination, which is why I say go back and look at your brownfield, you're going to have good enough acoustic coupling going forward. So, but I, again, for all the reasons I talked about in this webinar, I strongly advise you for any conduit installation to consider future path or micro technology bundled, because it has so many applications that are going to benefit you in combination with sensing.
All right. So, Dr. Paul, everybody is thanking you for this great session. And at the end, I can only thank Dr. Paul for this informative webinar and for his time. And we hope all the attendees enjoyed it and learned as much as I did today. Also, I want to thank Dura-line for accepting our invitation for this initiative. And I would like to thank also Mr. Yogesh from Dura-line for preparing everything and helping me in the last 2 weeks. Looking forward to welcome you all to our next webinar with Corning. We will announce all the details soon. And at the end, I will say Adha Mubarak and happy holiday for all the people in the Middle East and around the world. Thank you very much, Dr. Paul. Thank you very much for all the attendees. Wish you all the best.
It was my pleasure. Thank you.
Thank you, Dr. Paul. Thank you. Bye.